All right, so we're in topic 9, block 3 today. I believe we're on our goals and objectives today are to develop a probability model and use the model to find probabilities, find the probability of a simple event, and represent sample spaces for events. So we're going to start off in page 3 here. We're still exploring defining probability. And so basically what this page is set up for is to reinforce our practice of reasoning abstractly and quantitatively. So, what I want us to look at is this question dealing with Tyrone. Would you read that for us, Tashandrick?
Tyrone flips a coin 4 times and gets heads every time. So he gets an experimental probability of P. Heads equals 4 out of 4 equals 1. He wonders if his coin is somehow broken or flawed. In your group, conduct your own experiment. Find experimental probability of getting heads with 4 flips of the coin. Compare your results to the results of other groups.
All right. So, a while ago, I gave us a website. The website was the Flip Simulator. And so you needed to flip that coin 4 times. So, what'd you end up coming up with, Tashandrick?
I got heads 2 times and tails 2 times.
All right. I'm going to see what we get as a class. So, I'm going to flip this now. All right, so the first time we landed on heads. Remember, Tashandrick said he got 2 heads, 2 tails. So we got heads and tails. Got tails again. And tails again. So I got heads once and tails 3 times. So do you think his coins broke, or do you think that it just happened to go that way? All right. What did somebody else that went beside me and Tashandrick? What were y'all's results?
I got 2 heads and 2 tails.
All right, so you got the same as Tashandrick. Did anybody get 4 heads in a row like he did?
I got 4 tails.
Oh, okay, cool. Anybody else have any different results? Anybody have anything like me? Like I had 1 heads and 3 tails?
That's what I had.
Cool.
I had that too.
All right, cool. All right, so you're supposed to write down what you got for question 1 in your workbook. That's what it should look like. Should say probability block 3. And then the next page should look something like this. So we're on page 277. Does that sound right to everybody?
Yes, sir.
All right. So you're supposed to flip a coin 4 times and record your results. And so it says, how does your experimental probability compare with the experimental probability of your classmates? So we had 4 people that had heads, tails, tails, tails. How many people had heads, heads, and tails, tails? I know Tashandrick said he did.
I did.
And Najela did. So that's 2 people. Emma said that she had 4 tails.
I did.
Lainey is the same as Najela and Tashandrick. Does that sound right?
Yes, sir.
All right. And then I don't think we had anybody that had heads, 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 heads. So make sure you write that down for question number 1. All right, so looking at this, Najela, can you read this for us, please, ma'am?
How does the number of trials affect the experimental probability? Use animation to answer this question. The theoretical probability of getting heads on a fair coin is 0.5. Use the buttons to conduct different numbers of trials. How does the experimental probability compare to the theoretical probability as the number of trials increases?
All right, tell me this. Why is the theoretical probability 5/10 or 50%? Does anybody know?
Because it's a 50-50 chance.
Correct. It's a 1 out of 2 chance. So if you did 1 divided by 2, you're going to get 0.5, right? So we're going to do, says we can do 10 trials. So if we look at the first one, we got heads. Then we got tails. 3 tails. All right, so out of 4, we got 1 head and 3 tails. That's what I got a while ago. So out of 10 tries, it seems like this coin's more likely to do what?
Land on tails.
Mm-hmm. But you think if we kept flipping it, it would, it's possible that it could start landing on heads and not landing on tails?
Yes.
I think it is. It's one of them things that you never really know until you continue to do it. So it's still, we landed on heads a little bit more, but it's still landed on tails more than heads. So if you had this quarter and you were betting somebody that it would land on heads or tails, which one would you probably pick?
Tails.
Yeah, I would probably pick tails too. Even though it's a 50-50 chance, I think I would go with tails because every time that we do this, there's a how many percent chance of landing on tails. If it's a 25% chance that you're going to land on heads, what's the chance that you're going to land on tails?
75.
75%. How'd you do that?
Because I know that 25 plus 75 equals 100, and then since heads is going to be 25%, then I just knew that there would be 75.
All right. Anybody got a question about that? Okay, so what we've done is we've looked at this by doing just one flip at a time. All right. So what I want us to do is I want us to look at 100 flips. Right now we've looked at 20 flips. So what I want to see is if we go to 100 flips, do you think the experimental probability is going to be closer to our theoretical probability of 50%? Or do you think it's still going to be the same? Well, theoretically, that's stating that the chance of landing on heads and tails is a 50% chance. So the more times we flip this coin, the more likely we're going to get our experimental probability closer to the theoretical probability. So let's flip this 100 times and see where we're at. I'm thinking we're going to be somewhere around 0.4, but we'll just see. All right, so that's a 50-50 right there on the 10. It's 30 flips. 40, 50. So when we flip the coin 100 times, what happens? Like right here, it says,
on heads goes up.
say that again, Haley.
The percent of it landing on head goes up.
Yeah. So, I mean, when it says, how will additional trials affect the probability? Well, what happens? The experimental probability becomes closer to what?
The theoretical.
Correct. Correct. Because the more times you flip it, the closer it's going to get. You know, if you only do it once or twice, you could land on tails 2 times, or you could land on heads 2 times, and it's going to look like the theoretical probability really doesn't matter. But whenever you start getting into 100 or 1,000 times or something like that, then you're going to really see that you're getting pretty close to that theoretical probability. So, based off of this, it says for a fair coin, as the number of tosses increases, the experimental probability of heads stays near 0.5. And that's what we found out already. So I want you to think about something else. If the coin was weighted so that the coin landed showing heads twice as often as tails, what would be the new probability?
100 0, because it would always land on heads.
You're close. Think about this. 2, it's going to land on heads twice as often as tails. So that means that for every 3 flips, you would land on heads twice and you would land on tails once. Does that make sense? So, say for instance, we kind of broke this out in a chart. So we said heads, we're landing on it 2 times. Tails, you're landing on it once. Right? Well, heads would be for if we landed on it one more time. And does everybody see how that's happening?
Yes, sir.
So when you're looking at this, it said, how could you find out the new possibility or new probability? So how could you do that? Because it says that you're going to land on heads twice as often as tails. So Emma said that would be like close to 100%. What do y'all think? Anybody know? No one's answering. How do we find the probability? What do we do?
multiply.
Think back to it. How do we find experimental probability? Nobody remembers? What did they do?
Divide.
The outcomes by the total number of flips, right? Is that right or wrong?
Right.
All right, so how many times did you flip the coin here? We landed on heads 2 out of how many times?
3.
Correct. Which equals what?
0.66667.
Correct. So I'm going to just do that. What if we did 4 out of 6? Would it be the same thing?
Yes.
Yeah, it's going to be the same thing each time. So here, that 6 out of 9 is going to give us the same thing. So what happens to the chance of landing on heads? Does it go up or go down if it's weighted? Yeah, it went up. It went up. Almost 17% over that 50%, right? Does that make sense, Emma?
Yes.
Cool. All right. So I think when you were looking at it, you were thinking maybe it's like 2 divided by 1 would be 2, or 4 divided by 2 would be 2. So you were looking at it as 100% instead of looking at it as you still flip that coin for the heads 2 times and the tails 1 time. Is that what you did or not sure?
Yes.
Okay. All right. So how can we use experimental probabilities to judge the fairness of a game? I want you to think about that. How can you use experimental probabilities, what we just did, like taking a number of outcomes divided by the total number of tries, to judge if a game is fair or not? And is it important to conduct a large number of trials, or should you just do like 1 or 2? So think about like theoretical probability and experimental probability and answer that question. How can we use experimental probabilities to judge the fairness of a game? And is it important to conduct a large number of trials? Somebody can at least give me a yes or a no.
Yes.
Hey, well, yes to what?
You can check if it's fair or not.
Correct. All right. And so we do that by checking that experimental probability and seeing how close it is to the what? Starts with a T. We talked about it in class.
Theoretical probability.
Yes. Perfect. All right. Let's take a look at our question number 2. So on 2, Chris uses this spinner and he spins it 20 times and records his results in the tables as shown. Does everybody see that?
Yes, sir.
All right. So it says use a pencil and a paper clip to simulate spinning the spinner 20 more times and add your results to the table. So what you can do is you can take a pencil and a paper clip, or a pen and a paper clip, and you can put the paper clip right here on the bottom and you can spin it. Okay. Or you can go to a simulator that does A, B, and C, and you can spin it using your mouse on your computer if you want to. And that'll allow you to answer question number A. And then you'll be able to complete B, C, D, and E based off of that. So this is something that y'all can do on your own. And right now what we'll do is we'll go over our guided practice questions 1 through 6 together. Layla, will you read that one? Layla Gar.
You have discovered the new Super Selection grocery store. At the store, customers guess on which fruit the spinner will land. If they get it right, they will win a pound of the fruit. Every choice is based on a decision using probability. You want me to read the bottom again?
Yeah, please.
Okay. One of the games you have been selected to play is a spinner game. Before spinning, you must identify the outcomes on the spinner. There are blank equal part sections. These are blank sections with an apple. There are blank sections with an apple, blank sections with a strawberry, and blank section with a watermelon. The probability of spinning a strawberry is blank out of 8.
All right. So, how many sections are they, and how do you find those?
There's 8 sections, and you can count them.
All right. And so, how many sections have an apple?
4.
How many sections have the
4.
strawberry?
3.
And how many have a watermelon?
1.
Okay. So it says the probability of spinning a strawberry is what out of 8? What would we say?
3 out of 8.
Do y'all agree with that? Good. Perfect. Does anybody have any questions about how that works? Anybody remember what Haley said we could do to find out our answers? What'd she say we could do? Started with a C. Help him out, Haley. What'd you say we could do?
Count the section on the wheel.
Yeah, just count the sections on the wheel. All right, looking at this one. Haley, go ahead and read this one.
You watch 40 customers spin the spinner. You record the results of the experiment in a table. Drag the tiles to show the experimental probability of spinning each fruit. Show each probability as a fraction and as a percent.
All right. So it says we landed on the apple 18 times, the strawberry 15, and the watermelon 7. So what do we need to do, class? What do we do to find the experimental probability? We talked about it earlier today. We have to take the number of times something occurs, and Tashandrik said, and you have to divide it by what?
The total amount of time.
The total number. So what is the total number here?
40.
40. Good. How do we get that? How do we find the total? Somebody said it was 40. How did you get that?
Because it says you watch 40 customers spin the spinner.
Yeah. All right. And so what do we need to do to find our fractions? How many, what would be our fraction for the apples?
18 over 40.
Good. And so how would you determine the percent? What would we have to do that?
Divide.
Yeah, just divide, because this is 18 divided by 40. So you just take your calculator and do 18 divided by 40. What's that going to be?
45%.
Yep. And you just multiply that by 100 and it changes it to percent. So we get 45%. All right. What do we need to do for our strawberries?
Divided by 40.
Good. And what would I need to do to find my percent?
Divide.
Correct. I got to take my numerator and divide it by the denominator and then multiply it by 100. So what would we get?
37.5%.
So what does that mean the last one has to be? Do I need that calculator anymore? No. What's it have to be?
7/40, and the percent would be 17.5.
Perfect. Because 45 plus 37.5, if you were to take those and subtract it from 100, it's going to leave you with 17.5. And it's the only other option that you can do. Let's see if we got time to do number 3, and then that'll just leave y'all with doing 4, 5, and 6. So it says, think about what you have learned about conducting an experiment and analyzing results. Which of the following statements are true? Select all that are true statements. So the first statement says, an experiment involves actually doing something, like spinning a spinner or tossing a cube. Do y'all agree or disagree? All right. The larger the number of trials, the closer the results will be to the theoretical probability. After today's results, do you agree or disagree with that statement?
I agree.
Good. The results for each outcome will be the same during an experiment. Is that what happened today? No. Why did that not click? There we go. All right. The total number of trials is the denominator in the probability fraction. Is that true or false?
True. False.
All right. We got a false and we got some trues. So, Najela, explain what you think.
I think it's false because, like for each outcome, I don't think it's going to be the same during the experiment.
All right. Yeah, that one. Yeah, this one's out. This one's false. But right now we're talking about the total number of trials is the denominator in the probability.
Oh, I was looking at my bad. I'm sorry.
Oh, you're good. So do you agree with that statement or disagree?
I agree.
All right. So this is the total, and this is the denominator because it's at the bottom of the fraction. And what do we put at the top to find our probability?
The number of times it occurs.
Yep. Anybody got any questions about that?
No, sir.
All right. So what would we say? Is that true or false?
True.
Correct.
True.
All right. A smaller number of trials is better for analyzing experimental results. What do y'all think?
False.
I think it's false also.
False.
Good. Perfect. All right. So this is going to conclude our lesson today. So you have to complete question number 2 in your workbook. Remember, we're on page 277, 278-ish. And you have to complete your guided practice questions 4 through 6 if you haven't done so already.